In this video, we're going to build a simple logistic regression model. First, we'll go through the maths. Secondly, we will implement this model in Python using NumPy library. And finally, we will test it with breast cancer dataset from scikit-learn. This is fairly easy, so we achieved 98% accuracy. Notice that this is not an educational video, so I may make a lot of flawed points in my video. So feel free to correct me. And now let's go through the maths. Okay, so suppose that we have m instances and n features right here. So for logistic regression, we assume that there is a linear relationship between the variables and the logits of the probability. So let me show you guys what does that mean. So right here we have something like theta transpose multiplied by x equals something like z. So z is the logit of the probability. It will go something like this, as far as I understand. So this is the linear relationship. And it does look very weird if you're not very familiar. So let me show you guys a more familiar example. This is a linear equation, right? And a product term of a linear equation is something like alpha 1 x1, alpha 2 x2 plus something like alpha nxn if there's like nx, n number of x's, and then plus b, something I call an intercept. So this can be rewritten in the linear algebra format, which goes something like alpha 1 to alpha n multiplies by x1 to xn. And for the b part right here, it is an intercept. And in fact, these can be represented into matrices, but right now I won't represent this as matrices because, well, just make it simple. So these are two vectors, right? So b can actually go inside here, something like alpha 0, which in case when all of the parameters right here equals 0, then we have this parameter to multiply by x1 to xn and sum together, which will equals b. So this is a product term of, a product way to represent linear relationship. And this actually goes something like alpha transpose multiplies by x. So it looks very similar, right? Now it's familiar. And the reason why we don't have any b right here, as I've just told you guys, the intercept will just go into the first columns right here or any other columns in order to yield the same result, so that we don't have to represent another like matrix right here, which is kind of like nonsense. It's time consuming. So let me just remove all these things. Okay, let's come back to our problem. So right here we have a linear relationship, but what about this? This is called an odd. The thing inside the bracket right here, it's called an odd. An odd is basically a different way of representing probability. So for example, I say that the probability that the weather may rain tomorrow is 80%. So it goes something like P equals 80%. And the odd is just P over 1 minus P, which is, I'll say it like, this is 0.8, right? Over 1 minus 0.8, that is 8 over 2, that is 4. So 80% that tomorrow's weather may rain. So I'll say in other language, that is the odd that there will be a rain in tomorrow morning is 4. Just different way of saying it. So the beauty of this is that, how do I delete? Oh gosh. I'm back. Paint just stopped recording for some reason, but I'm back now. So we're here, right? So I was talking, the beauty of this equation is that you can take the exponential of the two part of the equation, which goes something like e to the power of z equals pz over 1 minus pz. This is very beautiful, and the reason is very simple. Let me show you guys. So suppose that, sorry, just move this part right here. We'll have pz equals e to the power of z minus e to the power of z multiplies by pz. And then we move this back here, take the factor of pz outside, we'll have something like pz multiplies by 1 plus e to the power of z equals ez. And basically this is pz equals e to the power of z over 1 plus e to the power of z. And minus this part too, sorry, divide this part and this part to e to the power of z, you will have 1 over pz plus 1. So this is 1 over e to the power of minus z plus 1. This is actually the sigmoid equation. And the beauty of sigmoid equation is that the graph of it will look something like, this is 0. Sorry, I should have this thing up a little more. This is 1. This is 0. So the graph of this equation will look something like this. This is the graph of the sigmoid function. And the beauty of this, oh sorry, this is not 0, this is 0.5. The beauty of this is that it always lies between 0 and 1. So for linear regression, there can be like a line like this, right? So the probability can be up to positive infinity or negative infinity. And we don't want it, because how can a probability be more than 1? Like you cannot say that I am 200% sure about that. Like if it surpassed 1, it should be capped at 1, right? But then it will not represent that it's more assured about the probability right that. So this actually solved the problem. It's kept the probability between 0 and 1 in a very beautiful way. So let's come back. Oh, and by the way, if you use Desmos to graph the sigmoid function, which is something like, let me do this, okay. 1 over 1 plus e to the power of minus x. Well, you see this graph right here. It looks very beautiful. Okay, let me delete this and let's come back. So once again, let me just remind you guys, we have m is the number of instances and n is the number of features. And we have just proven that pz equals 1 over 1 plus e to the power of minus z, and z is actually just theta t multiplied by x, right? Okay, so now the problem is that if we come up with a set of parameters, how do we assure that that set of parameters is true? Or in other words, when we know, when we have the data, how do we know that that set of parameters is the optimal set of parameters for the variables to achieve the probability which we have already known? So it's not so hard. We have something like the likelihood function, which is very interesting. I'll show you guys right away. The likelihood function of this will be something like L theta x equals, so the chance, the PZ, the probability that it's true, then like if, how confident is it to say that it's true? So it's will power 1, right? Y at the position, I'll say something, oh, this is actually, no, I missed some important part. This is the multiplication of I numbers of like features inside from 1 to m, because we have m instances. So this will be p of xi to the power of yi multiplies by 1 minus pxi to the power of 1 minus yi. So this is beautiful because, for example, if you're like extremely sure that this should be 1, this should be, because we are doing like binary classification, which means it's either 0 or 1, right? 1 is true, 0 is false. So 1 means that it's like a student is a good student, 0 means it's a bad student, for example. So something like that. Let's come back here. Then this, for example, you're extremely sure that that student is a good student, and the data tells you that that's true, he's a good student. Then it goes something like the model is 99% confident about this, and it's to the power of 1. So what is the incompetence? The incompetence is 0, 0.01 and to the power of 0, which is actually 0.99. Which means it's extremely sure about this. How beautiful that is. However, let's say, what should I say right here? Let's say you're not so sure about it. For example, like that is a very good student, but the model says that this is a very bad student. So it will go something like, oh my god, I come back here. It'll go something like 99, that this is a very good student, but the model says that it's a bad student. So it is 001 to the power of 1. That is 001, which is no. The likelihood is very low. So this formula captures the likelihood very delicately. And how can we derive whether the set of parameters is true or not from this formula? So at first, we should simplify it beforehand, because this is still using the raw numbers, which is kind of not good for the models. So you can actually take the natural logarithm of both sides. Let's say this is L of theta, because, well, oh, this is actually not theta right here. I wrote something wrong. This should be something like theta. Should it be? No, it should be Lx, right? Yeah, it should be Lx only. It should be it should be L theta only. So the natural logarithm of the likelihood function, I'll just denote this as L, normal L, equals. This is multiplication of I from 1 to m still, and this is the natural logarithm of this part right here. So notice that there are power right here, and this is a multiplication which can be derived as summation of natural logarithm, which becomes something like equals to the sum of, this is multiplication because now we turn it into sum, so it will be this annotation right here, and this is m. So this actually becomes yi multiplies by the natural logarithm of pxy, right, plus 1 minus iy, what else, multiplies by natural logarithm of 1 minus p to xy. Oh, right here I wrote it incorrectly. This should be zy, not xy. zy, 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 zy. Yeah, it looks pretty messy. Never mind. So now because you cannot, like, from the likelihood function, it just tells how confident, how likely it is that that number is 1. So you kind of maximize the likelihood or minimize the likelihood, because that will just either make the output all ones or all zeros, which is not what we're looking for. That is absolutely wrong. So we have to derive a loss function from this likelihood function. And interestingly, if you, because, should I say, because now, now, um, you have the likelihood function and take it logarithm, but like when you sum it together m times, it will be scaled up to m. So you have to take 1 over m, right, to like normalize it. And because this basically tells how likely, like how true it is to be the actual number, like the target values. So the loss function, we don't want to evaluate how true it is. We want to evaluate how wrong it is. So we're going at the opposite direction, which means we have to take the negation of the likelihood function. So the loss function will look something like, I'll just call it j theta. So it's 1 over m of the loss function, sorry, the likelihood function right here. And now we just have to take the partial derivative of the loss function over theta at any I value to find the optimal theta for that I value, which is fairly simple. Let me show you guys. So at any I values, it will go something like, this is gradient, right? Gradient is actually partial derivative at a, sorry, for a specific variable. So we have gradient j to theta is 1 over m. And now we use the chain rule. So this is gradient of theta. Sorry, this is, oh yeah, this is correct. Theta, and there is p inside here, right? So the likelihood function depends on the sigmoid function right here. So it will be LP, and the sigmoid function is depending on, what's it depending on? On z. And what is z depending on? Z is depending on x right here. Sorry, z is depending on theta, not x, my bad. X is fixed because we have x already. X is a fixed number, it's a constant. Theta, and this is at value I. We iterate like columns by columns, so it's at any, like for each student is a different I value, right? And there are m students, so I runs from 1 to m. So let's see, how do we solve this? So let me rewrite it right here. Okay, let me rewrite it right here. So for any, this is actually L. So for any L of I over pi, L at any position I equals H I, right? Is that so? Oh, yi, sorry, equals yi multiplies by p at xi sigmoid function plus 1 minus yi to multiplied by, I forgot the logarithm right here, my bad, over logarithm of 1 minus pxi. That's it. Okay, so now we have this function. So in order to take the derivative over p, it will becomes
something like yi over pxi plus, sorry, this is an x, this is z. I always forget this. Plus 1 minus yi, I is by minus 1 minus zi. Is that so? So let's simplify this. This will become 1i minus 1i multiplies by pzi, and this is okay. So this is become 1 right here. This will become yi minus 1. So plus yi pzi plus pzi. This is 1 minus pzi multiplies pzi. This will become something like yi plus pzi. That's it. That's interesting. And this is pxi, sorry, pzi multiplies by 1 minus pzi. Okay, very interesting. Very interesting. I need to make this longer. How do I make this longer? Please. How can I? Yeah, that's right. I wanted to make it even longer. Paint is like so bad. Paint's not good. I don't like paint. Okay, never mind. Let's come back. So we have this right here, right? Okay, I think that's correct. Yeah, that's correct. That's pretty solid. Oh, I made a mistake, don't I? Didn't I? Yeah, I made a mistake right here. It should be minus. That's it. Okay, so for p, gradient of p to z, it's pz equals 1 to the power of 1 plus e minus z, right? Let's zoom this out. So gradient of p to z would just be minus 1 of 1 plus e to the power of z squared multiplies by e to the power of z. This is, so gradient of z of e to the power of z is actually e to the power of minus z multiplies by minus 1, and minus 1 cancel out, so we have e to the power of z over 1 plus e to the power of minus z squared. And this looks quite familiar. Is it? It does look pretty familiar to me. Okay, so this is e to the power of minus z over e to the power of minus z multiplies by 1 over 1 plus e to the power of minus z. This is pz, right? And this is minus 1 plus 1 plus e to the power of minus z over 1 plus e to the power of minus z multiplies by pz. And this is actually minus pz, right? Okay, minus pz, it makes sense. So it's actually pz multiplies by 1 minus pz. Is that so? Is that so? Is that so? Is that so? Yeah, that's right. So it's pz multiplies by 1 minus pz. And finally, what is that? It's gradient of z over I. Where is it? Yeah, it's right here. So gradient of z over I It's basically gradient over I of theta transpose x. This is fixed. Theta I. So this is just theta, sorry, this is just xi. That's it. Okay, that's it. So let's say when we sum up together, a loss function will go something like theta I is equals, what is that? yi minus p to the power of zi over pzi multiplies by 1 minus pzi, and this is multiplied by pzi multiplies by 1 minus pzi. Oh, actually that's cancel out, and this is xi. So this cancel out, this cancel out, this becomes xi multiplies by yi minus pzi. This is transpose. Yep, that's it. So far so good. So we have this equation right here. This is our loss function. Sorry, the derivative of our loss function. Okay, so now let's start the Python implementation for this. Okay, let's get started. So previously, we have come to this equation right here. This is the equation of partial derivative of the loss function to theta. So we're going to implement logistic regression right now. Okay, let's open Python. And firstly, we'll have to install NumPy in order to do some linear algebra things. So you can download it using pip install NumPy like this. Okay, I miswrote it. Install. Okay, nothing is installing. Okay. Wait, why the requirement is satisfied? That's weird. Did I download it before? I don't know. Okay, let's come back. So firstly, let's come up with a framework for this model. We'll have the sigmoid function, right? So I just write it like this, return something. Secondly, we'll need to use gradient descent to optimize the parameters by minimizing the loss function. So basically, we'll just do gradient descent on this derivative of the loss function until it approaches really, really close to 0. So we'll have gradient descent right here. Return something. And in order to do gradient descent, we'll need to calculate gradient function. Okay, return something. And next, we'll need a predict probability function in order to, well, yield the probability because we're predicting. Finally, we need a predict function, which is a main function that compare the probability with a threshold to dictate whether the output should be 0 or 1. 0 or 1 because we're doing binary classification. Return something right here. So firstly, for the sigmoid function, the input will be z, right? Remember? So I'll just say something like result right here. So should I say is equal to sigmoid, right? No, not sorry. 1 over 1 plus exponential of minus c. That's correct. So secondly, calculate the gradient. Right here, we use this equation. So we have the input is x, theta, and then what else? X, theta, and then y. P is a sigmoid function, remember? And m is the number of instances, or in other words, the size of y. Okay, so firstly, have m first. M is the size of 1. And don't forget this. Theta, x, and then y. Okay. So return gradient, and gradient equals x transpose multiplies sigmoid function of x multiplies theta. This is matrix multiplication, and then minus y. Okay. All of this over m. That's it? Yeah, I think that's it. What else? So next, because we want to build a library, right? So I will put all of these into a class, and we call it logistic regression. Yeah. So for a class, we have to initialize some variables using this class. What should be the variable? I should just say self first, and then, oh yeah, theta. So initially just set theta to be none. So for this, we all need self inside here. That's right. And first, for gradient descent, what do we need? So gradient descent, usually in scikit-learn, we call this fit, right? Let me just clarify right here, gradient descent. And describe something right here like calculate the gradient for gradient descent. This is optimizing parameters using gradient descent. Okay, so for fit, of course we need x and y. And okay, so firstly, as I've said before, we have to turn x into x-intercept because we don't want to make it lengthy and time-consuming. So we do this by concatenating vector of 1 to the first column of x-intercept. It will look something like this. Concatenate of MP1s. So this matrix will have the rows of x, and it will have one column. So it will be x shape 0, which is the rows, and then one columns, and then concatenate with x. So same for this, we'll have theta. It will just be the same size as, sorry, it's had the same number of columns as x because, well, is it? Is that so? Oh yeah, that's correct. So this is theta intercept, and it will be initialized with zeros. Okay. Yeah, I think that's correct. Okay, interesting. Very interesting. So the row of theta should be equals to the column of of x because it's x multiplies theta. I think that's correct for now. So let's continue. Oh yeah, because we're doing gradient descent, so we're going to need things like number of iteration. Usually we set it as 1000. Learning rate, here is alpha equals 001, and then tolerance, which means how close it is that we allow the gradient to be to 0, because you know that when gradient is so close to 0, it will come to a certain state that there is no point optimizing gradient anymore. And the tolerance is the parameter that dictates how close gradient could be to 0. Here I would say it's 1e to the power of -8, which is really, really small, almost 0. So meter, things like this, and then alpha, tolerance. Is that so? I think that's it. Yep. For in range, we'll do num ether times right here. So theta will subtract itself to alpha multiplied by gradient, and we'll have to calculate gradient right here, which is calculate gradient, and then we input the theta, x, and then y. Okay, clarify something up here. This is x, b is x with intercept. Theta is also with intercept and is initialized at 0. This makes the model more stable. So, okay, if MP linear algebra normalization, which means the magnitude of this is gradient. When the magnitude of gradient is so close to tolerance, to tau, we'll just break this loop because there's no point implementing it anymore, right? Right here, we will return the theta, which is the optimized set of parameters. Okay. Oh, and by the way, this is x-intercept because, well, we're putting theta, which is also theta intercept right here. So now for the predict probability. Basically, the probability is a sigmoid function, right? And so basically, we'll just have to take in, just take in x, and then we use sigmoid function. Oh, and by the way, we'll have to implement x-intercept. So let's take this line right here and put it right here, and then we have xb multiplies by theta. Again, this is matrix multiplication. So I don't think that we need the result, right? Okay. Yeah, I think that's it. So finally, for the predict function, you'll also only need x, right? Yeah, only need x. And you return the predict proba of x compared with a threshold. Oh yeah, we should let threshold as a parameter that can be modified. Right here, we'll put it right here. Okay. Okay. So if this is greater or equal to threshold, we'll just return true or false and convert it to 0 or 1 using s-type int. So output is either 0 or 1, right? And for the gradient, there is a better way to, well, make sure that the model is not overfitting by adding something called rich regularization or lasso regularization. But right here, we'll just add rich regularization, which does something very simple like grant gradient from 1 onward because the 0 column is intercept, remember? So we'll apply the regularization by lambda reg equals 0. So lambda reg will run will be between 0 and 1, with 1 is really heavy penalty on overfitting things, sorry, on overfitting likelihood. So lambda rec over m, why is it still having, oh yeah, I misspelled it, lambda, okay? And this multiplies by theta, which also runs from index 1 onward, because 0 is intercept. 0 column is intercept. Okay, so we have to put lambda rec inside here as well, and also inside here equals 0, and lambda rec. That's right. Self. That's it. I think that's it. Oh, and yeah, right here. Because when z is too big or when z is too small, exponential of z can go to either positive infinity or negative infinity, which causes overflow. So you can cap this to like 500 and negative 500 to prevent that from happening. Cap z to prevent overflow. Okay, I think that's it. And now we should test this model. So far, so good. I'll just write, oh, sorry. I will just write something here for more description. Output the probability that the output is 1. Compare the probability with the threshold to dictate final result. So far, so good. Okay, now let's have some problem and I have to record this again, but it's fine. Let's create a notebook to test our program. You can install the packages by pip install scikit-learn, because we're going to need something for scikit-learn to test, and ipykernel for Jupyter Notebook. That's it. So first let's check if it's working. Kernel, virtual environment. Let's see if this works. Oh. Okay, it's working. From scikit-learn dataset, import load breast cancer. Dataset equals load spread cancers. There are data and target inside. So we have data and target. Just store them inside here as well, and target. Data shape. What's wrong? Oh, it's target. 569 instances with 30 features. Kind of interesting. This is a lot for just a small data set like that. So next we're going to split the data, which we're going to need train test split. And by the way, we're going to need standard scaler for scaling data. And finally, accuracy score for evaluate the accuracy. is data set. This is for splitting data. This is for scaling data. So first, we're going to split the data using train test split by doing this. Data target, and the test size will be 20%, which is 0.2. Let's see if it works. Right, this is extreme shape. Oh no, this is actually not what I'm talking about. I'm talking about this. So 455 instances for train and 114 for test. Okay, now we're going to scale it up because, well, model works better when they're scaled, when the data is scaled. So scalar equals standard scalar right here, called fit transform for this. And okay, sorry, kind of the same for X test, but transform only to prevent overfitting. Finally, we're going to test. Oh yeah, I forgot to import the model. And we're going to need import lib to refresh the model at any time we change it. Okay, that's right. So, okay, I think I should put it here. I'll call it LR model, which is, center active cell. So we're going to fit X train scaled and Y train, and we're going to predict the X train scaled. Let's see if there's an error. Okay, cannot interpret one as data type. A equals empty. So let's try this line. Concatenate brackets with X. Once this, okay. Oh yeah, this is wrong. So let's see. Firstly, this should be deleted, and then this whole should be bracket like this. So change this line as well because we copied. Another error, clip missing one required positional argument. So the function has something wrong. Is it? Oh yeah, I forgot to put Z right here. And operands cannot be podcasted together. Oh, this is matrix multiplication. Okay, it's working. Let's call this predict train. Okay, predict test. And finally, let's test the score. Y train, Y test. Oh, actually, this is train. Train accuracy of train egg. This should be, I know, 100%? For real? It's overfit. It's overfit for sure, but why? I don't think it's that good. Wait, what? Really? Strain, transform. Wait, what? How? How is so good? Oh yeah, this is why. We just... That's so dumb. Scaled and scaled. Oh no, sorry. This should be Y prediction train, and this should be Y prediction test. Oh, 98%. 396, 9. Okay, to optimize it, I think we can do something like this. Num iter equals 100,000. Alpha equals 001, 001, and tau equals 1e to the power of -8. And finally, lambda reg is something like 0.8, so that it can penalize the overfitting factors. Let's see if it's better. Nope, it's not better. Reduces to 7.8, for example. And let's see. I really want to make it better than that. 98%. Holy moly. Let's test it one more time. See how it goes. 100%. So at present, it is performing really well. It's almost always above 98% on a test set, which means it generalizes very well. See? So it is our model, logistic regression. And this data set, I think it's also has a very good linear relationship between the variables and the logit as well. That's why it's behaving so well at present. So thank you so much for watching. I think that's it for the video. That's all. Hope you guys have a nice day. Fantastic day. See you.